Michelle Baker, Managing Editor of Quality. We're here today at Max in Nashville, and I'm with Trevor Campbell, the Sales Development Manager of Microscopy at Zeiss Industrial Quality Solutions. So, welcome, Trevor. Thank you for being here today.
Thanks, Michelle. Appreciate it.
Yeah. So, Zeiss recently released its Manufacturing Insights Report, which highlighted the importance of measurement and metrology across manufacturing industries, including aerospace. So, can you tell us, how is metrology evolving to meet these demands?
Sure. So one of the core sort of competencies at Zeiss is that we want to be well connected with our customers. They're job number one when it comes to us handling the industry as a whole. So recently we did a very large study with a huge population of our customers, try to get more information from them about what matters. What trends are they seeing? What are the challenges they're facing? And how can we as a quality company help them meet those demands? A pretty heavy contingent of that was in the aerospace industry, which happens to be one of my focuses at Zeiss. I lead a team of people focused on our aerospace customers. So there's a really healthy amount of valuable information in that insights report that we've been able to learn a lot from and go back to our R&D team and make suggestions for on ways that we think we can improve our processes and in turn help their processes in the field.
That's great. So, of course, the other big buzzword people are talking about is AI. So with artificial intelligence entering manufacturing now, what specific roles is AI playing in improving aerospace accuracy?
That's a good question. There's a number of different ways that we're kind of adding to it right now. Some of them are more throughput based, where we're finding ways to generate results faster. Some of that is through like image reconstruction in non-destructive testing, specifically our X-ray microscope, our Versa. We can improve scan times by interpreting data as it's coming in using artificial intelligence, where it's able to blend together the different slices that it's taking faster to give you a much faster scan time and a faster time to results. There's other techniques that we use it for when it comes to sort of pattern recognition or image analysis, both in our microscopes as well as our CT X-ray systems. On the CT X-ray side, we have a defect detection algorithm that we are able to train based off of sort of known defects to where it can recognize those in the sample as it's finding it. So they're automated. So it's not something that somebody has to, sit there and comb through a bunch of images as it's taking these X-ray slices and say, okay, that looks like a void that shouldn't be there. It's finding it in real time without the operator having to intervene at all. There's a similar process on our microscopy techniques where we can train it to look at, different advanced materials, things that are not homogeneous. Batteries are a really good example, where the different layers, they're not distinct. They don't look like, a striped t-shirt where it's alternating colors and it's very easy to have the computer say, oh, well, that's a layer, that's a layer, that's a layer. They're non-homogeneous. So some of the layers are, spotted or have different colors or contrasts in them. And traditional segmentation has a really hard time picking that up. It wants to look at every individual color and contrast in there and pick that up as its own feature, rather than looking at it homogenously, where we say, okay, this entire pattern is actually one layer. We can teach it, hey, this pattern is one thing, not individual things, so that it's able to analyze the image and segment it how it's supposed to be segmented. So if we're looking at all those different slices of layers that aren't homogeneous, it knows what's a layer and what's an individual feature. The same is also true on samples that are like really low in contrast, for instance. One of the bigger examples is also in battery materials, is that the powders themselves they're gray and they're very low in contrast, especially if you're looking at them in a scanning electron microscope. And being able to detect those grain boundaries will let you size them. That size is very important depending on the chemistry in the battery that you're trying to achieve. Really anything that has low contrast is a really good application to let AI train the model and help the operator improve what they're doing. So you can get to results faster with a lot less manual intervention from an operator.
Yeah, it's so interesting. People talk about, the future with AI, but of course there's so many that are already well underway and have been going for a while. So
yeah,
it's amazing. So advanced materials are another major theme for aerospace. And could you tell us how our manufacturers maintain precision with harder or more complex materials?
Yep, so that kind of piggybacks into the microscopy artificial intelligence analysis. There's a number of different applications that are sort of difficult to be able to detect in an automated manner. More and more of our customers are looking to try to take as much manual decision making out of the process for a couple reasons. One, to make things more repeatable so that as you continue to run samples, you're getting the same types of results every time. But also to free up that person to be able to do something else rather than having to, sit there and look at every individual image that they're finding on the microscope, having to drive it around manually and hunt down these features. A lot of our systems can be automated to where both the movement of the microscope as well as the imaging techniques are built into what we call a job routine, a workflow of sorts that's a certain step of processes in a row where we can have it find something, take an image of it, and then segment it out using that artificial intelligence, whereas in the past somebody might be manually driving the instrument around and then having to potentially even just measure point to point or try to draw around a feature to get sizing on things. So with the artificial intelligence, we can train it by basically almost like Microsoft Paint, where you kind of go in and kind of paint by numbers. You say, okay, this is one feature, this is another feature, this is another feature, this is the background of that material. And then it'll recognize based off of different images we fed it and paints it on those different areas which part of that is which part of the image, and it can segment that out, give you things like area percentage, porosity, coating thickness, anything that you might want to automate on a more advanced material. And the more advanced materials get, some of these things are really hard to detect. Certain alloys, the grain boundaries and things that people might be looking at for grain structure or hardness, they're really fine and hard to detect. Imaging contrast techniques help with that, but they're still difficult for a traditional image segmentation method to detect. That's where AI comes in, where training it helps make it more repeatable so the operator doesn't have to do a lot of manual point clicking.
Mm-hmm. Makes sense. So kind of on those lines, I feel like a question everyone always is asking is, could AI ever replace human quality engineers? What's your thoughts on that?
Yeah, that's always a hot topic, and I think that AI gets a lot of negative connotation in the industry because people are worried that it will replace humans. The way that we're enabling it is not meant to replace someone so much as help them and make their job more efficient. So initially, someone was having to go in and draw and things like that. The operator's never going to go away in that aspect. They're still going to have to teach that instrument how to help detect it, and they're still going to have to analyze the results and look at them. But it's making it so that it's much, much more repeatable and it's more accurate, even more accurate oftentimes than the human eye, because that AI analysis it's learning as we're going. We're training it with more information. It's getting better at doing it to where now that operator, they just need to focus on getting it the best image possible, and then it can focus on giving you the best analysis. So we're making it so that the operator has a much easier time getting to their results, not removing the operator from the equation.
Good. So just another technology question. What technology do you think aerospace manufacturers should be investing in today?
If I had to pick one, it would probably be CT scanning. CT scanning is probably one of our fastest growing fields, and it's becoming more and more capable. Our systems are what we refer to as metrology grade CTs. We call it our Metratome for metrology, basically. The system uses a fixed detector where because we're not constantly adjusting it, it stays calibrated. The goal of our instrument is to help you find those features, but also to measure them accurately. So CT is capable of doing a wide variety of things, not just finding defects, but also, measuring features that we can't get to with maybe a more traditional measuring technique, like a coordinate measuring machine or even a 3D scanner, where you're only looking at what you can see from the outside. More and more geometries, especially with the growing applications for additive manufacturing, there's a lot of features on these parts that weren't achievable through traditional milling or casting techniques. We can We can get hollow cavities in something in one cohesive, uniform part rather than an assembled piece. So being able to detect internal geometries on something without needing to take it apart is a big help, especially if it's something that is made in one piece and doesn't come apart. You have to cut it apart. So a lot less waste when you can take a component, set it inside of a CT system, let it run a full scan, and then measure any of the internal features that you couldn't see otherwise. The other technique that I think would be really helpful for people, and we see a lot of growth in, is automated 3D optical scanning. We have some systems that use both laser scanning and structured blue light, where we're able to automate a lot of that three-dimensional measurement and scan parts in full. And even beyond that, we can start to automate things like part loading. We've got a feature called the batch processing system, or BPS, that goes with our scan boxes, where basically a robotic tower that sits to the right of the 3D scanning system, and it'll automate the feeding of parts into it. So once those routines are set up, the operator just has to load up that BPS system, and it will continue to feed parts through while the system is measuring it and then rotating in and out of new components. So it enables, again, operators to go work on another project. So the more and more we can automate things and make the inspection more accurate and take the user out of the sort of intervention in needing to manually do things, the faster companies can put out parts and the higher throughput that they can work through measuring.
Yeah, that all makes sense. Kind of speed things up, keep them as accurate as possible, and automate whenever possible.
Yeah, throughput rates are increasing more and more in the industry, and companies are wanting to inspect a higher volume of parts. The more and more advancements they get in the field, parts are becoming more complex, and certain things are enabling us to go new places, and those kind of parts need to be checked 100% before they go out in the field. So the amount of inspection and percentage of inspection that companies are doing is rapidly increasing.
That's comforting to think of for aerospace, so that makes sense. Can you share an example of a challenge that you maybe saw one of your customers facing and how you dealt with it?
Sure. So we've definitely had some challenges on the 3D scanning side of things. Some of that is just that, parts can be quite large. Our scan box systems are very modular in that we can basically create them as big as they need to be. Things like aircraft fuselage sections, full vehicles, anything of that size. A lot of times, people were using techniques that were either much more manual or they had to do them in sections where maybe you're using something like an arm-based scanner and you're kind of tethered to an area and you can only do so much of a footprint at a time. Something like a larger scan box where you're talking maybe multiple robots and multiple detectors, it's able to do that entire part automated, where it's moving the entire robot potentially back and forth on a chain system where it's driving back and forth, and then the robot moves independently on that. So we can do much larger parts with way less intervention and way less total programs, where it might take you a while to program it, but once it's programmed, put your part into the machine and run through it and let it automate that. Another challenge we've had recently is just denser materials in aerospace, either just through the material itself or just the sheer geometry of the component. Things like turbine blades on the aero side, for instance, have kind of been a challenge on that CT scanning side. And we just released a new 320 kilovolt system. So higher power kV source. So we're able to get through denser and larger materials. And we've had a lot of very positive results with that with our aerospace customers since that system was launched. We just got our first demo system installed in the field at our Quality Installation Center in Webster, Michigan. And we're running parts for customers right now on it. And things have been going really well with it. We're excited to get that into the field and start showing it to more customers to show what a system with higher punching power can do.
Oh, sounds great. So are there any certain obstacles you see in the aerospace industry facing? It seems like the challenges are always going up with, accuracy and more inspection. But are there any particular obstacles you've noticed lately?
Throughput and measuring volume is probably one of those biggest ones again. Just more and more, things are needing to be more accurate and higher levels of inspection. Another big one, which is in my microscopy field, is what they call technical cleanliness, where customers are taking a critical component and they put it through a washing step and then filter out the wash solution. And they're actually looking at that filter for debris. And you can automate that inspection through our microscopes, where we can basically tile together a very large stitched image of the entire filter and then use potentially AI techniques or basic image segmentation to determine where the particles are, how big they are they metallic or not? And you can even go beyond that and do this in one of our scanning electron microscopes and actually get elemental information. Those systems read the X-ray spectra that's coming off of the particles from the electron beam in that microscope, and it can tell you not just where that particle is and how big it is, but what it's made of. What's the composition of it? What percentage is this? What percentage is that? Is this tool steel? Is this copper? Is this dirt? We can find all of those things out by looking at those filters. And in critical components, especially like nozzles and things in jet engines, cleanliness is extremely important. A little bit of debris in there could potentially cause a catastrophic failure in the industry. And we want to help our customers prevent that. And we want to make it so that doing that inspection is simple and easy and automated, to where they've just got to make the filters and we can spit out the results.
Sounds good. Okay. Well, my last question was just about the future. So where do you see the industry going in the next 5 to 10 years?
Definitely a lot more CT and 3D scanning. I think people are looking for a lot more information on their parts, not just at that higher volume, but what can we detect that we weren't even looking at, in the beginning? Things like porosity through CT scanning. Some of that might have been done before, but maybe at a lower volume, or somebody was physically cutting apart the component and looking at it under a microscope. A lot of that can be done in situ effectively with a CT system, possibly even inline. We're seeing a lot of growth in inline inspection right now, where, as these measuring volumes and demands go up, somebody wants results even faster, and they've got a great inline solution for companies who want this built right into their manufacturing process, so they can, attain information like that porosity measurement or quick dimensional measurements on the inside of these parts in a much more real-time manner, so they know if something needs to be tweaked in process, and it could be adjusted much faster than it could be otherwise.
Okay, well, I think that's all the time we have, but is there anything else you want to mention or include here?
No, I think you did a really good job covering a lot of the needs of the industry, and Zeiss is committed to helping our customers achieve all those goals.
Sounds good. Okay, thank you, Trevor.
Thank you, Michelle.